Here I'm on the Giant Muffin problem, number 4. There are quite a few things to read here. First, there's this description of the reaction. Sodium bicarbonate decomposes. You've actually seen this in the fire extinguisher lab to form sodium carbonate, water, and carbon dioxide. Carbon dioxide gas is good for bakers. It causes doughs to rise. All right, so here we go. We'll start with, as it suggests here, it says start with the balanced chemical equation. That's a good place to start. I'll write it over here. We'll start with sodium bicarbonate, NaHCO3. I'll leave room for coefficients. Decomposition means you just heat it, and it turns into these products. One of them is sodium carbonate. Leave room for a coefficient. Sodium carbonate, you'll have to think about it. Use your periodic table. But you should come to the conclusion, Na2CO3 is sodium carbonate. The other two are easy, water and carbon dioxide. Water, carbon dioxide, CO2. All right, that's the chemical equation that results in this nice muffin here. And we'd have to balance it. So it's tricky because oxygens are all over the place. But sodium is not. Sodium is just here and here. So 2 sodiums need to be balanced with a coefficient of 2. Let's hope everything else balances. 2 sodiums. 2 hydrogens. I see 2 hydrogens in the H2O. 2 carbons. One of them is here, and the other is here. So there are 2 carbons and a total now of 6 oxygens. I see 3 right here, plus 1, plus 2. That is 6 oxygens. It is a balanced equation. So although it might seem intimidating, it's not that bad. Now we can do a little bit with this ideal gas law here. Okay, ideal gas law has these 5 letters. Pressure. Do we know what pressure this is? Well, it says baked at normal pressure. So unless you're at high altitude, the pressure in your oven is likely to be very close to 1 atmosphere. We're trying to calculate how much CO2 gas is needed to inflate the muffin. It says, look at the picture. Here's the picture. Start with a muffin batter, 400 liters. That's kind of liquid. Then you make some gas, and suddenly it's this big, huge muffin here. Woo, 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 woo. 1,000 liters of muffin. Most of that's gas, CO2 gas. So it's really the difference between the 1,000 liters and the 400 liters that is the CO2. I'm writing that as 600 liters. Moles of CO2 is what we'll be calculating here. So I'll just leave that as N. Don't know that, but the ideal gas law will help us calculate it. R, always know R, it's a constant from the periodic table. D, must use Kelvin. Okay, so what do we know here? Let's read again. Make a giant muffin. Muffin will be baked at a temperature of 175 degrees Celsius. That's a typical oven temperature if you've ever done baking. Okay, so let me do a little calculation in the margin here. 175 degrees C plus 273 will get me a Kelvin temperature. Okay, so I'm seeing 448 Kelvin is equivalent to 175 degrees Celsius, which is equivalent to 350 degrees Fahrenheit. All right, we have all the numbers we need now to do the calculation. Okay, what quantity of baking soda would be needed to make this happen? First, I'll do the ideal gas law. PV equals nRT. Scientists often do this. Well, they'll rearrange the equation. If I isolate N, it will be PV over RT. This is not essential, so if you've done it a different way, that's fine. But we have all the values for P and V and R and T, so it should be possible to calculate N. Go ahead and do that if you haven't already. Pause the tape. Okay, so I've filled in my numbers here with labels. And now I'm doing algebra calculation. I do need a calculator. 0.082 times 448. I have 36.7 on the bottom. I'm not labeling these numbers, but I will label my answer. I have N is 16.3. And since N is moles of CO2, I know the label. Moles CO2. Boom, boom, boom. Okay, that's not yet an answer to the final question, because I'm looking for what quantity of baking soda would be needed. But I can now put that with my balanced equation. So let me do that. 16.3 moles of CO2 corresponds to, I don't know how many moles of baking soda, but I can easily calculate that. So I'm hoping you see that it is a 1 to 2 mole ratio, 1 to 2 mole ratio. So I will kind of take a shortcut here and say, I know what this is. It's 32.6 moles of baking soda. All right, so that's just using the 1 to 2 mole ratio here. And that's why you balance your equation in the first place, to give you the mole ratios. Easy. Okay, so this is an answer. So you could just circle it and say, that's my answer. What quantity of baking soda would be needed? 32.6 moles. But I will encourage you and hope that you will try to figure out, well, how many teaspoons is that? Because bakers use teaspoons, and it would be kind of fun to calculate how many that is. So my answer was 548 teaspoons. So see whether you can get something close to that using your periodic table and your best stoichiometry skills. And then enjoy thinking about that giant muffin. How tasty would it be to have a huge 1,000-liter muffin?